Hello everyone, my name is Paweł Gora. I'm a founder and CEO of the Quantum AI Foundation, a board member of QWord and coordinator of QPoland, which is a Q cousin within QWord. I will tell you later about all these affiliations, but first of all, I would like to tell you that that would be the first lecture in the quantum computing session. The title is Introduction to Quantum Computing. So in fact, this would be the introduction to the theory of quantum computing. My second lecture, or the second part of this lecture, will be focusing on applications of quantum computing and building quantum computing ecosystem. The next lectures will be focusing on quantum computing algorithms and quantum machine learning, but these lectures will be given by Anna David and Oskar Słowik. So let's start. You can see that I mentioned three of my affiliations, so Quantum AI Foundation, QWord, and QPoland. So I will briefly explain why I mentioned three affiliations here, and I will tell you more about them in the second part of my lecture, focusing on building quantum ecosystem. So the Quantum AI Foundation is a charity organization aiming to support development and collaboration in science and new technologies, especially AI and quantum computing, but also other fields of mathematics and computer science and science in general. We organize Warsaw Quantum Computing meetups, QPoland workshops, and several other events, so you can check them on our website. QWord is a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. So it's not a formal or legal organization, but there is also a foundation established in Estonia to support QWord. But it's rather a network of local groups like QPoland and also Quantum AI Foundation. It's also an organization supporting QWord. So I will also tell you more about QWord and its initiatives in the second part of this lecture. But I would also like to mention a few words about QPoland. So QPoland is a Q cousin, so it's one of these local groups within QWord, and we also organize workshops and several other initiatives like quantum computing hackathons or contests on popularizing quantum computing. So I will tell you more about this initiative in the second part of this lecture. So let's start discussing quantum computing. So as I said in the first part of this lecture, I will give you an introduction to the theory of quantum computing. And in the second part, I will tell you about some possible applications of quantum computers and about building a quantum computing ecosystem in Poland and worldwide. All right, so what exactly is quantum computing? The simple answer is that these are computations according to the laws of quantum mechanics. So of course, the real and the more advanced answer is more complicated, but let's now just focus on this simple answer, right? So these are computations according to the laws of quantum mechanics. So it's not easy to explain what actually quantum mechanics is, but let's just first try to understand what the word quantum actually means. So in physics, a quantum is the minimum amount of any physical entity, physical property, involved in an interaction. And the fundamental notion that the physical property can be quantized is referred to as the hypothesis of quantization. And this means that the magnitude of the physical property can take only discrete values consisting of integer multiples of one quantum. So we'll see an example soon. But it's also important to know that when we talk about computations, then of course we may talk about algorithms and computational complexity. and we can try to prove that our algorithms are correct, but we should also remember that the computation is a physical process. Computations are conducted on real physical devices, real computers. So computations are governed by the rules of the physical world, which is inherently quantum. Now coming back to the explanation of quantum mechanics, everything started more than 100 years ago, and the Max Planck's postulate is considered to be one of the milestones in developing the theory of quantum mechanics. And this postulate basically says that the electromagnetic energy could be emitted only in quantized form, right? So now we have this example that we have a physical property like energy of the photon or magnetic wave energy in this case. And it looks that it can be emitted only in quantized form, right? So we have the n, which is an integer number, and we have Planck's constant, which determines what's the value of the energy, of course. And we also have a frequency of a photon or electromagnetic wave. So we can see that it's not true that for each value of a frequency of a photon or electromagnetic wave, we may have any arbitrary energy emitted, right? So the energy may be emitted only in quantized form. Okay, it may have very interesting consequences in physics, which brings us to the development of quantum mechanics and later also to quantum computations. Another example that the fact that we run our computations on a physical devices may have some consequences is the Landauer principle, which basically says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, such as erasing one bit of information. Right? So we should also remember about it when we run computations, right? That we cannot just run our computations for free. There is a minimum possible amount of energy that is required for some logical operations. Okay, so Richard Feynman, the famous physicist, in his work, There's Plenty of Room at the Bottom, said that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. And in fact, there may be certain advantages. Okay, but is it really true that we cannot build computer elements much smaller than they are now? So I guess that some of you have already heard about the Gordon-Moore's law, which says that the number of transistors in a dense integrated circuit doubles about every 2 years. And Moore's prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But in 2015, Gordon Moore himself said that I see Moore's law dying here in the next decade or so. And Intel, a company developing processors, CPUs, also realized that the pace of advancement has slowed. So now this doubling is not once per 2 years, but once per 2.5 years. But they then also observe that this trend will continue thanks to hyperscaling. But can it continue forever? Well, it turns out that if this density of transistors and also the size of a transistor will have to, so the density will have to be doubled once per 2 years or 2.5 years, then it would mean that in about 2035, 2040, a size of a single transistor should be of the size of a single atom. And then the transistors will be governed by the rules of quantum mechanics directly. And in fact, even much earlier, most likely the transistors will not be able to just operate in a way that they operate nowadays. And in fact, we can even already observe some impacts of such a small scale, and it's getting more and more difficult to just make improvements in this area. All right, but what will happen if our transistors are in a scale of a single atom? Richard Feynman, the same famous physicist, mentioned in 1983 that now we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function. The ones move around, the zeros move around, and finally, along a particular bench of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But can we do it? That's the question posted by Richard Feynman. And yeah, you can see that here in this statement there was a mention that potentially we can run computations on atoms, right? So potentially, even if our transistors are of the size of a single atom, then potentially we can run some computations. Of course, the transistors should be built in a different way than they are built nowadays, but maybe we can still run some computations. But can we do it? That's the question asked by Richard Feynman. So since we have a lecture today about quantum computing, then and this question was posted almost 40 years ago, then I guess that you can imagine that potentially we can already build some quantum computers. And in fact, there are several companies working on building quantum devices on which we can run quantum computations. Google is one of such companies. So here in the figure, in the image on the left, you can see a bristlecone, which is Google's quantum processor, one of the Google's quantum processors. And on the right, you can see a cartoon of this device where each X, each crossing represents a qubit with nearest neighbor connectivity. But of course, nowadays we have much more approaches to build quantum computers, and I will later also tell you about it more. All right, but what actually is a quantum computer? What are the differences between quantum computers and classical computers? So in case of classical computers, we have bits and classical gates. So bits may just have values 0 or 1, and classical gates just take these bits as an input and just compute the output, right? So we may have classical gates like AND or NOT. So these are very popular and well-known classical gates which can just transform bits and produce another bit or bits as an output, which again may be an input to the next classical gate. But in case of quantum computers, we have qubits and quantum gates. So what's the difference? So I mentioned that in case of bit, the state has a value 0 or 1. So mathematically, it's something relatively simple. It's just an element from the set 0, 1. But in case of quantum computers, we have qubits, and the state of a qubit may be in a superposition of ground state 0 and 1. So mathematically, it's a unitary vector of the two-dimensional Hilbert space over complex numbers. So it seems to be quite complicated. So also in case of classical computers, the state is determined, so we can know exactly whether the state is 0 or 1. And the state can be changed from 0 to 1 and vice versa using the logical gate, classical gate NOT. But in case of quantum computers, to get values 0 or 1, we can do a measurement which breaks superposition, and the probability of getting 0 or 1 depends on the qubit and depends on the state of a qubit, which is this unitary vector of the two-dimensional Hilbert space over complex numbers. And our quantum gates just modify qubits, and they just modify the probability of getting 0 or 1 after the measurement. This is a quantum superposition. So the 0 and 1 are our pure states represented in a ket or Dirac notation, and these are orthonormal, so vectors of the orthonormal base of the quantum system, right? So these are the pure states, and A and B are complex numbers, such that the squares of their amplitudes are probabilities of getting 0 or 1 in a measurement. So the squares of their amplitudes should sum up to 1, of course. Right, and now we have a quantum superposition. So we have a coefficient assigned to the pure state 0, and we have a coefficient assigned to the pure state 1, and these coefficients just determine the probability of getting 0 or 1 in the measurement. So according to the arithmetics of complex numbers, there exists a complex number such that when we can multiply A and B by this complex number, and in a way that will not change the sum of squares of amplitudes, right? So the sum will be still 1, but the coefficient assigned to 0 will be a real number, right? And we can transform our quantum state to spherical coordinates. So how we can do that? Okay, so we can also represent our quantum states on a sphere that is called a Bloch sphere. So all the points on this sphere are just good quantum states, which might be in a superposition of pure state 0 and 1. So 0 and 1 are just points on this sphere, which are just antipodes, right? So in case of classical computers, a single bit may be in a state 0 or 1. So these are these antipodes on the sphere. But in case of quantum computer, the state of a qubit may be just any point of this Bloch sphere. And in fact, we can see what's the transformation from this superposition, from this arithmetic representation to a geometrical representation of a Bloch sphere, right? So I mentioned that we can multiply our quantum state by a complex number, and that will not modify the quantum state. In fact, so the probabilities of getting 0 and 1 will be still the same, but the number assigned to the pure state 0 will be a real number and not a complex number, not only a complex number, right? So in fact, that would be a value from 0 or 1, from the range 0, 1. So it is a cosinus of some angle. And when we determine this angle, then we can also determine what should be the value of the second number assigned to the pure state 1. And based on that, we can also find the second angle determining our quantum state, right? And it turns out that these two angles determine the point on the Bloch sphere. So sometimes in case of quantum computing, we also says that quantum computing is a journey on a Bloch sphere, at least in case of a single qubit, right? Because our quantum states are just points on our blocks on the Bloch sphere, and our quantum gates just transform these points. So just transform one point on a sphere to another point. And usually the most popular quantum gates are just some kind of rotations or transformations which are composed of several rotations of this block sphere. Okay, so here are some notable examples of quantum gates. So, for example, we have a Hadamard's gate, which builds a superposition of state 0 and 1. So this pure state 0 and 1 can be transformed to the quantum states in which the probability of getting 0 and 1 after the measurement are the same, right? So these probabilities are just 0.5 in theory, at least. And this is the same for the pure state 1. So initially, the probability of obtaining the value 1 after the measurement was just also equal to 1. But after applying this Hadamard's gate, the probability will change. We also have the X Pauli gate, which just corresponds to some kind of logical knot, to classical gate knot. So it just transforms pure state 0 into pure state 1 and pure state 1 into pure state 0. And similarly, we have Pauli gates Y and Z. I will later tell you why we call these gates X, Y, and Z Pauli. So these gates just operate on a single qubit, but we may also have quantum gates operating on more than 1 qubit. So the CNOT gate is a very popular and notable example because it takes 2 qubits as an input, and 1 qubit is just a controller for the NOT or X Pauli gate operation on the second qubit. And it turns out that any quantum circuit can be simulated to any arbitrary degree of accuracy using a combination of CNOT gates and single qubit rotations such as X, Y, Z, and Hadamard's gate. Okay, so why we also talk about rotations, right? So here you have also a matrix representation of the Hadamard's gate. So if we assume, because I also mentioned that our quantum states are just also vectors, unitary vectors in two-dimensional space. So this two-dimensional space has two pure states, 0 and 1, which correspond to vectors 1, 0 and 0, 1. Right. So any point in this Hilbert space can be just represented as a superposition of this pure state 0 and 1, where we have coefficients being complex numbers, right? So when we just do operations in this Hilbert space, we just transform one vector into another vector, right? And for any such operation, or at least for any reasonable operation that we consider, we have we have a matrix representation, and because we want our transformations to be linear transformations, in fact, right? So also our pure states, which are a base of a Hilbert space, are also transformed to another base and to another vectors. And for example, so these linear operations can be also interpreted as rotations on our block sphere. So for example, the Hadamard's gate corresponds to a rotation of P about the axis X plus Z. Or alternatively, we may first rotate our sphere around y-axis by P half, and then we just rotate our sphere around z-axis by P. Right, so we may have arithmetic representations, matrix representations, and geometrical representations using rotations of a Bloch sphere. And these are matrix representations, a matrix representation, and also geometrical representation of X Pauli gate. So we can see the Pauli X matrix, but we can also interpret it as a rotation of P about the axis X. And as I have mentioned, the X Pauli gate just is a quantum equivalent of the node gate, because it transforms the pure state 0 into pure state 1 and vice versa. So in case of CNOT gate, the CNOT matrix is more difficult, but CNOT acts on 2 qubits, right? And it performs the NOT operation on the second qubit only when the first qubit is 1, and otherwise it leaves it unchanged. Okay, so so far we've been talking mostly on a single qubit or maybe 2 qubits at most, but the true power of quantum computing comes from quantum parallelism and the fact that in case of n qubits, we may represent 2 to the power of n numbers. So we may represent all possible combinations of 2 to the power of n numbers, in fact. So in case of n bits, we may represent only a single n-bit number, but in case of n qubits, we may represent 2 to the power of n numbers at the same time, because we can just assign a probability of obtaining one of these 2 to the power of n numbers after the measurement, right? So of course it might be complicated to modify the probabilities of getting each of these 2 to the power of n numbers, but this is in fact how quantum computations look like, right? So they are almost all about modifying probabilities of getting specific values after the measurement. So initially, when our quantum system is in a state in which we have just pure state 0, we can apply Hadamard gates to each qubit, so that after doing the measurement, we can get each of the possible 2 to the power of n numbers with the same probability. But of course, we can later modify this probability, and using CNOT gate and other gates, we may also make this quantum system entangled and even more interesting. But the important thing is that in a single run, we process all states at the same time. So we process all states present in the superposition. So here, this U is just an operation. It's just a quantum circuit representing some quantum operations composed of basic elementary quantum gates like X Pauli or Hadamard's gate or CNOT, for example. And then we just apply such quantum circuit, quantum operations to all the states presented in the superposition. And here is just an example, right? So here you can see a relatively simple quantum circuit in which we initially have 8 qubits. So their initial state was the pure state 0. And you can see that in case of several qubits, in case of qubits on positions 3, 5, and 7, we don't apply any quantum gate, right? So after the measurement, the state will be also 0 with probability 1. But in case of other qubits, we have some transformations. So for example, in case of qubit number 6, we apply the X Pauli gate, which is just our quantum NOT operation. We just modifies the pure state 0 and creates a pure state 1. So after the measurement, at the end, we'll also get the pure state 1 or the one with probability 1 as well. But the situation is more complicated in case of qubit 0, 1, 2, and 4, because in case of qubit 4, initially we have a Hadamard's gate, which just creates a superposition of pure state 0 and 1. If the state, so for this quantum state 0, when we apply the X Pauli gate, then we have state 1, and then we just trigger the synod gate, right? Because our quantum or qubit controlling the synod is 1, so then the values of qubits 0, 1, and 2 will be also changed from the pure state 0 to the pure state 1. But then this state 1, or quantum state part of this superposition corresponding to the pure state 1 will be again transformed using another X Pauli gate, so it will become 0 again. So after the measurement, in such a case, we'll get the value 0 for qubit 4 and the values 1 for qubit 0, 1, and 2. But we'll get it only with probability 0.5, because with the same probability, the pure state, or the state of the qubit 4 after application of the Hadamard's gate will be 1. So after applying this X Pauli gate, it will be 0, and it will not trigger the synod gate, right? So the values of the qubit 0, 1, and 2 will be still 0 at the end. But the value of the qubit 4 will be later modified again using X Pauli gate, so it will be 1, in fact, right? So then, again, with the probability 0.5, the value of the qubit 4 will be 1, while the values of qubit 0, 1, 2 will be 0 at the same time. So when we run computations many times, we'll observe that with probability 0.5 or close to 0.5, we'll get a bit representation of the ASCII letter P, or ASCII representation of the letter upper P. So 0, 1, 0, 1, 0, 0, 0, 0. Yeah, so here only the values of qubits 4 and 6 are 1. But with the same probability, or more or less the same probability, we'll obtain the ASCII representation, bit representation of the upper G. So it will be 0, 1, 0, 0, 0, 1, 1, 1. So here the values of qubits 0, 1, 2, and 6 after the measurement will be 1. So yeah, so with more or less probability 0, 0.5, we'll get this ASCII representation of the letter P, and with the same probability, we should get the ASCII representation of the letter upper G, and these are just my initials. So I just built a quantum circuit to just compute, in fact, my initial letters. So we can observe that here on 8 qubits, we are able to represent at least 2 8-bit numbers at the same time, in fact, right? So just after doing measurements, we are able to get only one of these 2 8-bit numbers. But when we run computations many times, then sometimes we'll get the ASCII representation of P, and sometimes we'll get the ASCII representation of G. Okay, and this quantum circuit was designed using Qiskit framework from IBM. So I will also later tell you about this framework, because this is one of interesting and also quite intuitive frameworks for designing and writing your quantum programs, designing your quantum circuits. All right, so why it is important? I said that in case of classical computers on n bits, we can process only one n-bit number at the same time, while in case of quantum computers using n qubits, we can process all 2 to the power of n n-bit numbers. Another difference between classical computers and quantum computers is that in case of classical computers, the results are deterministic, so randomness is in fact a pseudo-randomness. But in case of quantum computers, we may have real randomness and we can easily sample from probability distributions, which are difficult for classical computers. All right, that was all about the theory of quantum computing that I wanted to present you in this first part of my lecture. I hope you enjoyed, and I invite you to watch the second part, which will be dedicated to applications of quantum computing and building quantum computing ecosystem.